Welcome to Spring LIB.
This is the answer to Chapter 12, problem number 37 from the Smith Organic Chemistry textbook. And this problem asks us to consider stearidonic acid and to consider some hydrogenation reactions involving stearidonic acid. So first we're asked for part A, what would happen if we were to treat stearidonic acid with an excess of hydrogen gas and a palladium catalyst supported on carbon? And so the answer would be exhaustive hydrogenation, or in layman's terms, every one of these double bonds is going to be hydrogenated. And so the backbone of the molecule is going to be exactly the same. And rather than drawing it complexly like this, we could just draw it in a straight chain form. But I think it's easiest to just draw it how it is originally, and just remember that all of these double bonds are single bonds now. And the carboxylic acid is going to be unaffected. So that's part A right there. So for part B, we're asked what would happen if we did the same thing, but with only one equivalent of hydrogen gas. And so the answer is we're going to get a mixture of four products. And these four products are going to be the four different possibilities for only one of these double bonds being hydrogenated. So bear with me for a moment while I draw all of these backbones. And then I will go back and fill in the double bonds to show you exactly what I mean. Okay, so there's two. Just have to draw two more. Oops. Oh, man. Okay, there we go. I apologize. Yeah, the lag got me for a second. Okay. There's three. All right. And here finally is number 4. All right. Sorry, I apologize. Pop-up antivirus renewal nonsense. Okay, so here's number 4. Okay, so what I mean by a mixture of 4 products, each of which is going to have one of the double bonds hydrogenated, is this. So we're going to get a mixture of all 4 of these products. So either the first double bond can be hydrogenated, but none of the other 3, or the second, but none of the other 3, or the third, but none of the other 3, or just the fourth can be hydrogenated and none of the other 3. And it will be a mixture of all 4 of these molecules because there's no control in this molecule. So we could envision a scenario where one of the double bonds is more susceptible to hydrogenation than the other 3. And so that one would obviously be preferentially hydrogenated. But there are no steric considerations here or substituent considerations that would increase the reactivity of any of these double bonds. So they're each equally susceptible to being hydrogenated. So if we use one equivalent of hydrogen gas, we're going to get a mixture that should, in theory, be these 4 molecules, and they should be present in equal amounts. So it should be 25% of each of these 4 molecules. And so that's part B. So for part C, we're asked to draw one of these molecules from part B, but with one of the double bonds isomerized to the trans version. And so I'm just going to put that up here. So one of the possibilities that we could draw for part C would look like this. So in this case, this double bond has isomerized to the trans version. And this second double bond is the one that got hydrogenated. So it's not there anymore. And then everything else about this molecule would be the same. So, okay, I am missing this double bond. Okay. Oh no, I'm missing this one as well. All right, so there we go. Okay, so this is a possible answer for part C. Again, we could make any of these the trans double bond, and we could hydrogenate any of the four as well. It doesn't matter. There's no specificity given in the question for part C. And so lastly, for part D, we're asked, how do the melting points of the following fatty acids compare? So stearidonic acid, the product formed in part B, and the product drawn in part C. And so the answer there is going to be that we are comparing stearidonic acid, which has 4 cis double bonds, the product in part B, which has 3 cis double bonds, and the product in part C, which has 2 cis and 1 trans double bond. So part C is going to be a higher melting point than part B, which is going to be a higher melting point than the starting material with the stearidonic acid, which I'll abbreviate as SM. And so that's the answer to part D, because again, the answer from part C is going to have 2 cis double bonds and 1 trans double bond. So that molecule is going to be able to pack in more tightly than either of the other two. So it will take more energy to make it melt. Next would be part B, just because it has 1 fewer cis double bond than the starting material. And so the starting material is going to have the lowest melting point because it is least able to pack tightly together. And that's the answer to chapter 12, problem number 37.